Okay, so welcome to the tutorial. Okay, so for the tutorial about the basis, we are going to do 2 questions. Okay, so let's do the first question. Okay, so we have the first question says, prove that the following set is a basis for R3. So we have B equals to 1, 0, 0, 1 minus 1, 0, and 0, 0, 3. So we have seen in the definition that a basis for a vector space is a sequence of vectors that is linearly independent and that spans the space. So we need to check 2 things. We need to check number 1, step 1, linear independence. Yes. And we need to check this step 2 is going to be the span. Okay, so linear independence, so the 3 vectors in B are linearly independent if C1 1 0 0 plus C2 1 minus 1 0 plus C3 0 0 3 equals to 0. Okay, 3 to 0 vector. So here you have C1 plus C2 equals to 0 minus C2 equals to 0 and 3 times C3 equals to 0. Okay, so it is already in echelon form, thank God. That means we are going to do back substitution. C3 equals to 0, C2 equals to 0, and C1, which is minus C2, equals to 0 as well. C1 equals to 0. So we have C2 0, C3 0, C1 0. So C1 equals to C2 equals to C3 equals to 0 means that B is linearly independent. Okay, so in step 2, we need to check data. Check that B spans R3. Spans R3. That means if we have we pick any element x, y, z in R3, it can be written as a linear combination. We can have C1, C2, C3, so that we can write that element x, y, z as a linear combination of the 3 vectors in the basis B. Okay, so let's write it down. So we have C1 1 0 0. We want to find those C's. Okay, that can help us to write the linear combination of the vectors in B. 0 0 3. So this is C3 equals to x, y, z. I hope you can see. This is C3. Okay, so we have C1 plus C2 equals to x minus C2 equals to y, and 3 C3 equals to z. Okay, so back substitution, that means C3 equals to a third of z, okay, c2 equals to minus y, and c1 which is equal to x minus c2 equals to x plus y. Okay, so c1 equals to x plus y. So c1 equals to x plus y. Therefore, for any vector x, y, z in R3, okay, there is c1 equals to x plus y, c2 equals to minus y, and c3 equals to a third of z, such that x, y, and z, the elements of the space, can be written as a linear combination of the elements in the basis P. C2, 1 minus 1 is 0, plus C3, 0, 0, 3. Okay, therefore B spans, okay, R3. So in conclusion, B, so that means, all of this means B is a basis for R3. Okay, so step 1 and 2 allow us to prove, so this is step 2. Okay, so step 1 and 2 allow us to prove that B is a basis, because B is linearly independent and B spans R3. Okay, we will do our second example here. Okay, so now let's work with a polynomial of degree 3. So question 2. Okay, so it says in P3, okay, prove that B is a basis, and our B is 1x, x squared, x cubed. You have seen in the previous video that B is called the natural or standard basis. This B is a natural or standard basis for P3. Okay, but now we are going to prove that it is a basis. So we need to check the two things. Step 1, check linear independence. Okay, so we have C1 multiplied by the first element, which is x, sorry, which is 1, plus C2 multiplied by the second element, plus C3 multiplied by the third element in the basis, plus C4 multiplied by the fourth element, x cubed, equals to the 0 polynomial, so 0x plus 0x squared plus 0x cubed, which is actually 0, okay? So here we have, yeah, I don't need the bracket, but it's fine. So the polynomial on the left-hand side is equal to the polynomial on the right-hand side, when the coefficients are the same. Okay, so C1 equals to 0, so the C1, that coefficient equals to the coefficient of so the constant of the left hand side is equal to the constant on the right hand side. The coefficient of x on the left hand side is equal to the coefficient of the x on the right hand side. So C2 is equal to 0. The coefficient of the x squared on the left hand side equals to the coefficient of the x squared on the right hand side. C3 equals to 0. And the coefficient of the x cubed on the left hand side equals to the coefficient of x cubed on the right hand side equals to 0. This is very easy. Therefore, B is linearly independent. Okay, so now let's check the span. Step 2, check that B spans P3, the space P3. Okay, so we want to find C1 plus C2x plus C3x squared plus C4x cubed. We want to find those C's such that any element in P, which is A, we can call it A, bx plus cx squared plus dx cubed, okay, such as any element in P3 can be written as a linear combination of the vectors in the basis P, okay? So here again, the constant C1 on the left is equal to the constant on the right hand side, so C1 is equal to A, C2 is going to be equal to B, C3 is going to be equal to C, and C4 equals to D. So that means B spans P3. We can find those C's, okay, for any element in P3. We can find C's. So in conclusion, B, so we can say therefore B is a basis for P3. Okay, so I'm going to stop here, and in the next video we are going to continue with the concept of representation. How do you represent a vector with respect to a basis in a vector space? Okay, see you.